Today's lesson video are going to look at physics electrostatic. This is lesson 102. Let us start. In the previous lesson video, we looked at the electrostatic force existing between 2-point charges. Now in this one, we are going to look at 3-point charges in one dimension. In this case, we need to know the direction. Now suppose the question says calculate the net electrostatic force on point charge B. What we need to know is that the scale to know the direction. Remember, electrostatic force is a vector. So the first thing that we need to do, we need to calculate the electrostatic force existing between A and B, and then we calculate the electrostatic force existing between B and C, since our main focus is on B. And then we look at the charges. Suppose we make sure that this charge is stationary, it doesn't move at all, or it's not allowed to move, and then we look at the direction of B due to C. We actually allow B to move. We know that the direction of B will be to the right. As we can see, the nature of the force between the two charges is force of attraction. So when you consider right as positive, left as negative, it means the electrostatic force between B and C will be positive. And then we ignore C, we go to A and B. We make sure that A doesn't move, and then we look at the direction of B. We can see that the force of attraction will actually make or cause sphere B to move this direction. And then we can confirm that the electrostatic force between A and B, or F1, will be negative. That is important. Let us look at the first example. Suppose we have this scenario. JKL is our spheres. J, it has -4 microcoulombs, K positive 6 microcoulomb, and then L is -8 microcoulomb. The distance of JK is 30 millimeters. The distance of KL is 60 millimeters. Now the question, calculate the net electrostatic force on K. The first thing that we need to do, we need to calculate the electrostatic force between J and K, which the equation is this one. And then we have 9.0 times 10 to the power 9. Then Q1 is 4 times 10 to the power -6. And then we have Q2 as 6 times 10 to the power -6. This is all over. The distance is 30 times 10 to the power -3 squared. So the electrostatic force between J and K is 240 newtons. We look at the direction. Since we have negative and positive, we make sure that this doesn't move. We can see that this will move to the left, so it means direction is left. We need to go ahead and calculate the electrostatic force between K and L. So electrostatic force between K and L is equals to K Q1 Q2 over R squared. KL is equals to 9.0 times 10 to the power 9. And then Q1, which is our K, it's 6 times 10 to the power -6. Then Q2 we have 8 times 10 to the power negative 6 all over the distance between their centers. It's 60 times 10 to the power negative 3 squared. We find that FKL is equals to 120 newtons. We look at the direction. It's negative and positive. We make sure that this one doesn't move. We can see the direction of K will be to the right, so it means the direction is to the right. And then from here, F net, the net force experienced by K, it's equals to the net force of JK plus the force of KL. Now in this case we need to consider the direction, so we can see that JK is to the left, so it will be negative 240. Since we take left as negative plus, we have 120 to the right, positive 120. Our answer is negative 120 Newton. When we conclude, this is 120 Newton to the left. So this simply means that suppose we want to draw a free body diagram of K. We have three forces. This one will be F JK, which is 240 newtons. And then this one will be F KL, which is 120 newtons. And then this is not drawn to scale, by the way. Our F net will be this one, which is 120 Newton. Let us look at another one. This is our second example. The question says calculate the net electrostatic force on P, which is this one. Now we need to calculate electrostatic force between PQ and PR. The first thing we need to do, PQ is equals to K Q1 Q2 over R squared to the power 9. Q1 is 2 times 10 to the power negative, no, actually it's 10 times 10 to the power negative 9. Q2 is 5.5 times 10 to the power negative 9. And then our distance, we have 2 times 10 to the power negative 6 squared. Our electrostatic force of PQ, we have 1,23750 newtons. Let us figure out the direction. Remember, we are focusing on P due to Q, so we make sure that Q doesn't move. Since we have positive and negative, it means the direction of P will be to the right. Then we move on. We're going to calculate PR. So F PR is equals to K Q1 Q2 over R squared. F PR is equals to 9.0 times 10 to the power 9. Then Q1 we have 10 times 10 to the power negative 9. Q2 we have 1.5 times 10 to the power negative 9, all over the distance. Remember, the distance is from P to R, so we are going to add the 2, which will be 8 times 10 to the power negative 6 squared. The answer is FPR, it's equals to 2109.375 Newton. Let us figure out the direction. We make sure that this doesn't move. Since it's positive and positive, it means its force of repulsion. This will move to the left. So the direction is left. Now we need to calculate F net on P is equals to F PQ plus FPR. Our FPQ we take right as positive. It's 123,750. It will be a positive term since we take right as positive, and then this one is to the left, which is 2109.375, supposed to be negative because it's to the left. So the difference of the two it's equals to 121,640.625 Newton to the right, since it's positive. Looking at the free body diagram, we are going to have P, actually it's F PR, and then we have, oh no, it's supposed to be FPQ, then this is FPR, and then the resultant, or the F net, will be this direction. That's it for this lesson video. This is Wahula SJ. Thank you very much.